Hi, my name is Gage DeZoort, and I'm a third-year PhD student in Princeton University's Physics Department. I work on the Compact Muon Solenoid experiment at the Large Hadron Collider, the LHC, and one of the projects I work on involves tracking charged particles with graph neural networks. I first want to motivate charged particle tracking, which is the process of measuring the trajectories of particles in the detector. Tracking typically occurs in the innermost layers of the detector, and in particular yields critical information about where the particle was produced and its subsequent direction and momentum as it traverses the detector layers. In roughly 5 years, the Large Hadron Collider will undergo a series of upgrades, entering into its high luminosity phase, the HLLHC. In the HLLHC era, there will be an unprecedented number of overlapping interactions per data taking period, which will pose a significant challenge to track building algorithms because they've been measured to scale quadratically or worse with the number of overlapping interactions. This highlights the need for us to explore new algorithmic strategies to reconstruct particle tracks from tracker data. One exciting paradigm, and the one I'm going to tell you about today, involves representing track data as graphs, subsequently using a graph neural network to help you predict tracks. Graphs are data structures that involve nodes connected by edges. Edges encode the local structure of the data in some way. Tracker data is naturally represented as a graph due to its irregular structure with a strong emphasis on the spatial connections between the hits. So you can turn your track data into a graph by simply mapping hits to nodes and track segments, or your hypothesis for them, to edges. On the left, you see a high-level view of how graph neural networks work. Essentially, GNNs take input data, represented as a graph, and then aggregate information in some pre-specified way across the graph, ultimately producing a new representation of the graph that's easy to do inference on. In particular, GNN-based tracking proceeds in three key stages. In the first stage, the graph construction phase, you simply build a graph from your underlying data. So here I've drawn two hypothetical particles moving through the detector, yielding hits and also an additional noise hit. So in your graph construction step, you would draw these purple arrows between the hits in your detector and come up with your initial graph. In the second stage, the inference stage run by the graph neural network, you would operate on each edge in the graph and predict the probability that it corresponds to a real piece of a track, a real trajectory. Here, of course, the green edges perfectly reconstruct the charged particle trajectory, so our GNN would have been pretty good in this case. In the third step, we build the tracks from the GNN predictions by essentially clustering the hits. As an example, I wanted to highlight some results from our recent paper studying the interaction network, which is a physics-motivated graph neural network that has been shown to have powerful performance on physics simulation in particular. In this case, you can see in the first step, we built graphs, and here we've labeled the true edges in the graph as blue and the false ones as black. This is truth information that is used to train the graphs. In the second step, we run the graphs through the interaction network, which then predicts whether or not the edges are true or false, whether or not they correspond to true particle trajectories. You can see here that we achieve an extremely high edge classification accuracy of 99.81%, corresponding to roughly 50 and 30,000 errors. In the last stage, we build the tracks using clustering algorithms. Here you can see a comparison we've done between two different clustering algorithms on the output of the GNN inference stage. You can see that we're quite robust to different sizes of the graph, which we modulate via energy cuts of the particles inside of the graph along the x-axis here. I did want to highlight, in conclusion, two future directions we're excited about. This interaction network that we've been studying is quite small relative to other GNN options and is therefore a suitable candidate for acceleration via field programmable gate arrays, which is something our group is quite excited about doing and is actively studying. In addition, we'd like to accelerate the graph construction stage on FPGAs. We're also interested in exploring novel GNN architectures, in particular for doing one-shot tracking, in which we compute all of these stages, producing tracks in one shot, in one single forward pass of a graph neural network. Thank you very much for your time.